Good morning, everyone. This time we look at a little bit more complicated problem where we have distributed load, and it's a uniform one. Not we don't complicate it that much. So we have this cantilever beam where we can see that has a negative oriented distributed load on top of the beam pointing downward. And when we calculate its resultant and put it at the centroid of that rectangle where it is there, we can see easily it's the area of the rectangle, very clear to understand. Again, the first step is calculate the support reactions, which you do here. Very simple using Newton second laws, and I will not stay that much on this one because I hope by now you know how to solve them. Um, Next step, shear diagram that we use, as we said, that free body diagram we just did in the previous slide, and now we focus on the uh, this equation on the jumping upward and downward, and this equation. So how we start? We look at the concentrated because it's about shear forces, concentrated forces. So at point A, that AY tells us pointing upward, we need to jump upward with W naught L, which we do right here. And then as we move to the right, we look at that differential equations we have. And at this moment, we can see that we have a um, uh, uniformly distributed load, which is negative, and it's that has that value W. So it's a constant load, in other words, from A to B. And I put there the sign is negative. We look at the two things, sign and magnitude. Sign is negative, and the magnitude, we know it is W naught. It's a constant. I apologize, I didn't put it here constant. I just put the value. So, in other words, being constant slope, it means that uh, uh, the curve should be a line of that negative slope. And it means that we start from this point and we go all the way to the right. Where here we are supposed to end with the zero at the end of the beam. But are we sure we ended there? So how do we figure it out? So again, we apply that principle that we take this equation and we integrate it. And this time we use the for us it's the function that varies from along the x-axis, the w, which means is the area under this yellow rectangle that you see here that I drew there, easy to calculate. And we are calculating V at point B. It's going to be equal with the shear force VA plus the change, which is the area of this rectangle. So when we are doing it, that will end up right there at zero. Again, in the area of the rectangle, I did use the negative sign of the W. Although here it's W naught, so please be aware of the negative sign. If it's going downward, it's negative, like we were uh, having in our convention. Now we use for the third step this diagram to just calculate the bending moment, and we can see that we use the again this at the left point we use this concentrated moment MA that we solved in the first step for it, and because it's counterclockwise, it means it's a negative one by convention. Or again, if you want to use that, as we mentioned very early in the notes, that by convention, if it's the beam is bended in such a way by the moment that the top fibers are in tension and the bottom fibers are in compression, that means that the moment is negative, which we either two of them will work. So basically now when we look at that, we have that jump downward with the value of the moment ma, and then as we go from left to right, we have to look at this equation, and that equation tells us two things. One, that the shear force is having a positive sign, and the magnitude, as you can see, is not constant anymore. It keeps decreasing as we go. So the slope of this bending moment, it's not going to be constant anymore. It's going to keep going down. With that, as we will see here, it's decreasing, as we said. So in other words, we are expecting a parabola this time, and we see that the slope everywhere in the parabola is supposed to be positive, and the slope is decreasing. So of course there are two cases here. I say in the class, one, you can build the parabola this way, or you can build it the other way around. But you can see that if we are building the other way around, like increasing from here, that exactly tells me that the slope is increasing, and although it's a positive slope, the slope is increasing instead of decreasing. So this way of building the diagram will be wrong, because we are supposed to start with the high slope here, and as we move in any point, the slope of the tangent on the curve is supposed to go all the way down. And by the way, at point B, because V is zero there, my slope is supposed to be zero. That is exactly what these equations tell me. Again, to calculate that value for the moment and be there, basically, we look at that idea with, well, we have to start from point A, well, like we said, and then we have to look at the change from A to B. And this means is the area under this curve of the shear force, which is exactly that, the area of this triangle, the yellow triangle that I put it there. And again, in this case is positive, the shear, this side, and this is the length of the beam. They're so easy to calculate, and we get the moment in B as being zero. I hope this again simplifies a clear way for you to understand beam theory for these types of problem. If you have comments or questions, please put them in the uh, comments below, or send me an email. Have a beautiful day.